I think I'm the only one here.
Okay. 1 minute. Let me see. So you try your hands on this problem. Given that y has a value of, given that y is equals 86889 e to the power of 2 e minus 06x, compute the value of sales, that is the dependent variable, the publicity expenses is 250. So what would the value of sales be? So just try your hands on that. Let's see. So that's the equation there. What is this? What is this? Okay, so we know that we are using this equation, right? This one, which is the one stated here. So we know that y is equals, no, sorry. We are using this one. Let's use this one. I want us to use this transformed one. This one. This one appears linear now, right? I want us to use this linear transformation instead of the original equation. Whichever one you use, you get the same, you get it anyway, but I mean, the purpose of transforming is to make it linear and simpler. Okay, so we know that natural log of y is equals natural log of k plus what? Bx, right? Is that right? That's this equation.
Yes, sir. Yes.
Therefore, ln of y is equals ln of, what is k? This is k. This 8, look at it from here. You can see that this 868895 is k, right? While b is this 2e e exponential minus 6. Okay, so this k is 868895. Hope you will know where this k came from our scatter plot, from the equation on the trend line. The equation we got on the chart of our scatter plot. Okay. What next? Plus, right? Plus bx. B is this 2e minus 0 times what? I want to see if you are following.
Times 250.
Thank you. That's times x, which is 250. Okay, so that's what we are going to. That's what we need to do there. So that's what it is. Okay. Right, so let's compute it now. So that's the figure it's giving us. Okay, what figure? What does this figure represent? I want to be sure you are following me.
It's 30.6 million for the sales, yeah?
No. Is it in millions? No. Because you expect it to be a bigger figure, right?
Yes.
That's why you are saying that now. But you have to understand that this figure is not Y. This is what we just got now, not Y itself. This is what we just got now. So how do we get Y? Y is what we are looking for, right? I hope, are you getting my point?
Yes.
Y is what we are looking for, not natural log of Y. So to get the Y itself, you have to use the exponential function of this figure. So this will be the sales. Why is it so small? Well, anyway, but this will be the sales. This is the estimated value of the sales. So we'll take a closer look at it so that we'll see what's happening. But don't forget that this is not the best model for this. We are just using it for the purpose of explanation. We saw that the linear model gave a better R squared value, right? Well, this is the sales it's giving us. Does it make sense? 250.
Doesn't make sense.
Because if you watch this 250, if you trace it, it's saying it will be somewhere here, which is not, which just doesn't make sense. Doesn't make sense. Oh, there's an error here. Look at minus 06, right? 06. What did I type here now? Supposed to be 2E minus 06. That's more like it. Yeah, that's more like it. Right? There was a typographical error there that caused that. So this is the figure. 1.4. Let's say we trace this 250 now. You see that it will be somewhere around here, right? If you are to extend this line, this is 250.
Yes,
If you
sir.
are to extend this line further, you see that it's going to hit somewhere around here, right? It's going to hit somewhere around here. which is
Yes.
1.4 something million. So it makes sense. Hope it's clear. Is it clear?
Yes, sir. It's correct.
Let's put exponential. Okay. The one we're using just now was even linear. Okay, so let's say 250, 250. If you extend it, if you extend this line, going to be somewhere here, which is still about the same. Okay, so this is how you use this. Okay. Now you do this if, for example, if you have a better arrow square value for exponential than linear, then you can use this equation. You can use the exponential equation. Okay. If you have a better result, a better one. But if linear is the best, it's better you use linear. Okay. In our case, I want you to also see the other one, the logarithmic. I use logarithmic. We have seen the exponential, linear. For logarithmic, for the logarithmic, you can see it says y is equals that. Of course, the arrow square here is very low, so we don't need to use this at all. Okay, but logarithmic is used when the value of x is very high, grows very rapidly compared to y. That's when we use the logarithmic. Okay, that's why the natural log function is used to reduce the x so that it doesn't grow too rapidly, thereby converting it to a linear form. Okay, so in a nutshell, what I'm saying in effect is this, that when you are doing regression analysis, you try to see the best, try to ascertain the best type of model to use. It's not always linear, may not always be the best, the model that suits the data the most. Okay? Yeah. So that's what we have been able to establish. So are we okay? Is it clearly understood? Understood?
Yes, sir. For me, it's clear. So,
Clear. Okay. Who else do we have in the house now? I think that should be you, Saze.
Yes, sir. I'm following. It's
Okay.
getting clearer, sir.
Okay. 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 So now the exercise I want to give you another exercise now. Now, suppose we're using the linear model. This would have been the equation. Okay. So now I want you to solve the same problem, assuming it's linear. Let me copy the problem down here. assuming we are working with this equation. Okay, so can you try your hands on this? Can you try your hands on this problem? So we compare.
Yes, sir. Let's try.
Yeah, just try it. So compare the answer with this one. I know the answer will be close anyway. So, like I said, since the R square value for the linear is higher, so 3%, 73%, 73.1, compared to exponential of 71. So we'll go for the linear regression, okay, which is this, which means we use this equation rather than using this one. So logarithmic is very far from it. That is 0.4. That's for the 6%. So it's quite low compared to this one. So you don't even consider this at all. All right. Yeah. So that is how that works. Okay. So knowing how to take that decision is very, very important. Okay. So I believe that is very clear to every one of us.